Robot cooking, transferring observations into a planning language. By recording the pose of the acting hand in a cooking scenario, a dataset is generated. First, predefined side actions are detected in this dataset using classification. The remaining frames are then clustered into main actions. Using this information, the known initial positions and virtual object tracking, a machine-readable planning domain definition language is generated. Recording the cooking process, how to generate the data. First, a cooking process must be recorded. For this purpose, all objects in the workspace are identified once before the cooking process. A motion capture system consisting of 7x13 cameras is used for the recording. During the process, the cook wears a glove with 3 passive markers placed on the back of the hand in a defined, fixed position relative to each other. These 3 points provide enough information to derive a pose. Continuous recording at 120 frames per second provides a trajectory of the hand. The recorded video shows the movement of the hand and its various poses while performing different tasks in the cooking process. All recorded data are basically poses with time stamps. Other variables such as velocity, acceleration and angle in relation to the tabletop were derived from this. A visualization of the absolute speed of the hand and its position in space already reveals some characteristics. Now a method will be shown how these characteristics will be worked out by an automated process. An initial structure of the dataset, identification of secondary tasks by using a classification. As seen before, the visualization of the movement already reveals the characteristics of some actions. Some short actions occur repeatedly, are very consistent in their execution and occur in every cooking process. These are, move, pick, place. To provide an initial structure to the dataset, a classifier is trained to identify these actions. For this purpose, besides the initial dataset, a training dataset is recorded. With the chosen classification method and parameters, the classifier is trained. This classifier is now applied on the initial dataset to perform the classification. As the result of classification, we now identified the side actions. This provides a basic structure to the dataset, allowing the analysis of the remaining actions to continue with reduced complexity. How to identify unknown actions? After the previous identification of the side tasks, the so far unknown main actions must now be found. Up to this moment, it is not known how many of these main tasks exist in this cooking process. Even if it seems clear to the human eye, the remaining frames, here highlighted in blue, must be divided into actions. This is done using clustering. Clustering searches the frames for similarities based on various parameters. In our study, a unique fingerprint is found for each action, consisting of the orientation of the back of the hand and its speed on the table plane. This fingerprint is used to assign the frames to a cluster, which corresponds to an action. Generate a PDDL, translating the knowledge gained into a planning language. In the next step, we combine all the collected information into a plan. To do this, we use the results of clustering, including classification. These are used to create sequences that summarize specific sections of the frames. By adding the initial positions of the known objects, we can now create a plan. Within this plan, we can virtually track the objects. A pick action causes this object, for example the cuke, to be in hand afterwards. A place action sets the new position of the object. The cuke now is on the cutting board. The unknown actions are described in a standardized way. In this example, the cutting is described as cuke is processed by knife on cutting board. The analyzed schedule is transferred to PDDL. A PDDL consists of a domain and a problem, which are transformed into a machine-readable plan using a solution algorithm. This serves as the bridge between the human demonstrator and the robot. The presented solution allows to translate a human-guided demonstration into a PDDL and finally to create a task schedule that can be executed by one or more robots.